Next one is feedback amplifier. In this feedback amplifier concept, what is the thing we are going to see is what happens to input impedance and output impedance. This is what we are going to see. The input impedance and output impedance, what happens in a feedback amplifier. So this is the amplifier with A gain, and this is the feedback network with beta. This is a sampling network. It can be shunt or series. This is a comparator or mixer network. It can be also shunt or series. This one is signal source. This one is RL is load. So this is structure of a single loop feedback amplifier. Okay. So let me show you this one. So VA is the voltage source. RS is the source resistance. RL is the load. V0 is the output. So here it is due to shunt connection. It is the V0 output voltage is taken and it is given in series to the input voltage. So we call this connection series shunt connection because the output we are having shunt, input we have series. Therefore, we call it as series shunt connection. Here, the output is series connected and input is shunt connected. Therefore, we call this one as shunt series connection. And here, the output is also seriously connected. The input is also seriously connected. Therefore, we call this as series connection. And here, the output is shunt, input is also shunt. Therefore, we call this one as shunt connection. Okay. So what happens in the series shunt connection? We call this voltage amplifier because the input is also VA, output is also V0. In shunt series connection, the input is current, output is also current. Therefore, we call it as current amplifier. Here in series connection, the input is voltage, the output is current. We call this as transconductance amplifier because it's I by V is equal to conductance. Therefore, we call this one as transconductance amplifier. Here the input is I, the output is V. So V by I is equal to R. Therefore, we call this as trans resistance amplifier. Shunt amplifier is known as trans resistance amplifier. So that is what here given, transconductance current voltage. Okay. So what happens to the input resistance and output resistance due to feedback? That's what we are going to see now. So we have a voltage amplifier AV in the forward path and beta V is the feedback amplifier gain. So what we have VA is the input voltage, RS is the source resistance, and due to VA and RS there is a current flowing II. This current flows through RI and produces a voltage drop of VE, and here we have V0, and this beta V0 is the voltage that we sample from output. Therefore, beta V V0 is equal to VFB. Okay, so this is the left hand side, and this right hand side, what we are going to have, VE is the input voltage, VE is the input voltage for the amplifier. Therefore, AV is the gain. Therefore, AV into VE is the output, and R0 is the output resistance, and V0 we are going to have from AV-VE. Okay, hope you understand the system what we have. Okay. So we are going to see what happens to voltage gain, input impedance and output impedance. So let us take this amplifier here. So V0 is equal to A into VA. So since R0 is very less, we can take V0 is equal to A into VA. Watch my cursor moving. Here V0. You can see V0 and this is AVI. So V0 is equal to AVA. VA is given by VS minus VF. So VA is given by Vs minus Vf. So we substitute here, and Vf is given by beta into V0. Here it is. So V0 is, we have taken beta times V0 to the feedback voltage. The feedback voltage Vf is equal to beta into V0. We substitute Vf here. So what we have, A into Vs minus beta V0 is equal to V0. We substitute the second equation in the first equation. We get A into Vs minus beta V0 is equal to V0. Therefore, AVs is equal to, here you multiply here, AVs is equal to 1 plus beta A into V0. So Vs by V0 by Vs is equal to A by 1 plus beta A. So this is the closed loop gain of the voltage amplifier. So this is V0, this is Vi, Vs. So V0 by Vs is equal to A by 1 plus beta A. A is the amplifier voltage, B is the feedback voltage. So A by 1 plus beta A is the gain, voltage gain. Now we have seen voltage gain. Now we are going to see about input impedance. What is input impedance? The input impedance is the one which is seen by Vs by Is, which is seen by the current Is. So Zin is equal to Vs by Is. We already know Vs from here. We already know Vs is equal to Va plus Vf. So we substitute Vs is equal to Va plus Vf by Is. Again, Vf is equal to beta V0. Therefore, Vf is equal to beta V0. Therefore, we substitute Va plus beta V0 by Is. Va plus beta V0 by Is is equal to Zin. V0 is equal to AVA. V0, this we know. V0 is equal to AVA. We substitute here Va plus beta A into Va by Is. Therefore, Zin is equal to, take Va common, which is this one, Va into 1 plus beta A by Is. Va by Is is equal to Ri, which is Va by this one. This Vi by Is is the current flowing through that. So Va by Is is equal to Ri. So Ri into 1 plus beta A. Now Ri is the input impedance of the amplifier. Zn is the input impedance of the closed loop amplifier. So that is the difference between the both. Ri, this Ri is the input impedance of the open loop amplifier. Zn is the input impedance of the closed loop amplifier. So what we are seeing here, Zn increases by a factor of 1 plus beta A. This is desirable because the input impedance should be high to avoid loading effect. Therefore, Zn is equal to Ri into 1 plus beta A. This is algebraic manipulation which you can easily achieve 1 plus beta A, which says that Ri is amplified by a factor of 1 plus beta A. Let us see output impedance. To find the output impedance, what I am going to do, I am going to Vs is equal to 0. I am going to make Vs 0 and I am going to supply a voltage V0 at the output. So this is the diagram which you have to see. When Vs is equal to 0, what happens here? We have already seen Va is equal to Vs minus Vf. If Vs is equal to 0, Va is equal to minus Vf. That is the point. One, Va is equal to Vs minus Vf. Vs is equal to 0. Therefore, Va is equal to minus Vf. If Va is equal to minus Vf, what is AVI? AVI is equal to V0 minus AVI by R0 is equal to I0. This is the second equation. What I am getting is V0 is I am supplying here. AVA is the input voltage. V0 minus AVA by R0. This is Kirchhoff's voltage law. V0 minus AVA by R0 is equal to I0. So accordingly, we apply this one. Therefore, since Vs is equal to 0, Va is equal to minus Vf. What is Vf? Beta V0. So Va is equal to minus beta V0. I substitute the Va value here from here. Therefore, I get I0 is equal to V0 plus A beta V0 by R0. Okay. What is Z out is given by V0 by I0. Therefore, if we take V0 by V0 in 1 plus A beta V0 by R0. So V0 get cancelled. We get R0 by 1 plus A beta. So here what we see, R0 is the output impedance of the open loop system. Z out is the output impedance of the closed loop system. Z out is equal to R0 by 1 plus A beta, which says that output impedance reduces by a factor of 1 plus A beta. This is the desirable one which we want because we want to connect more inputs to the output without loading. So that will be helpful if the output impedance reaches 0. Therefore, this Z out is reduced by a factor of 1 plus A beta. First one is a desired objective. In a voltage amplifier, where the input is voltage, output is voltage, transformation is given by AV by 1 plus A beta V AV. Input resistance is given by Ri into 1 plus beta V AV. Output resistance is by R0 by 1 plus AV beta V. So output resistance decreases, input resistance increases by a factor which is desirable one. Because if in series input connection increases input resistance, avoid loading effects of the input source. Let me show you. If Zn is high, II will be low because it will demand only lesser current. So this will be helpful when the input impedance is high. At the same time, R0, if it is less, more I out will come. So we can drive more output connections. Always high Ri is desirable and less R0 is desirable. Okay. Effects on frequency response. Here gain and bandwidth is equal to constant. So here what we see, gain of the amplifier and frequency. We have plotted in x-axis. Bandwidth without feedback. So bandwidth without feedback, open loop, we see the gain is high, but the bandwidth is less. See the gain value, it is here. The gain is high, but the bandwidth is less. Whereas if you see a closed loop gain, the gain is less, whereas bandwidth is more. Because gain and bandwidth is equal to constant, the increase in gain in open loop results in reduced bandwidth, whereas increase in bandwidth results in reduced gain in closed loop system. So this is effects on frequency response. It is desirable one because bandwidth increases as gain is reduced with feedback. Okay. So far we have completed the overview. And next one is branches of control. If you take branches of control, it is adaptive control, robust control, real-time control, intelligent control, servo control, regulatory control, nonlinear control, optimal control. These are the types of control system we have. What is adaptive control? If you see, when the plant or process parameter changes, the control parameter also changes with respect to plant parameter and maintain the desired response. So that is known as adaptive control. Adaptive control means the control parameter also changes with respect to plant parameter. In robust control, one controller is going to control many plants. That means a large variation in plant can be controlled by one single controller. This is known as robust control. If you take a real-time control, one example for real-time control is airbag system. In the airbag system of an automobile, every time if it has to airbag has to be released in 3 milliseconds, means every time repeatedly it should be airbag should be released in 3 milliseconds. Even if it goes to 4 milliseconds and 5 milliseconds, the accident may happen. Therefore, real-time control is more deterministic in nature. Intelligent control is incorporating human intelligence into the control system. Examples for this one is fuzzy logic and neural networks. Fuzzy logic and neural networks, if you put into the intelligence of the controller, then we call that as intelligent control. Servo control means the input of the control continuously changes. That we call that as servo control. Whereas regulatory control, the input is constant or zero. So we call that type of control as regulatory control. Nonlinear control, the system have nonlinear properties. It is difficult to control. Therefore, we will go for nonlinear approach. Next one is optimal control, flight optimization, flight trajectory optimization. So here we are going to have one objective and we have to choose the control parameters to reach the objective. Okay, applications. We have cruise control. Cruise control means speed control. Already we have seen active suspension system. So we are going to give a good suspension in such a way that the chassis will not have bumps. Next one is anti-lock braking system. So all of you know about anti-lock braking system. I think when the car brakes, it should be done in less time. So there we go for anti-lock braking system. Engine control unit, already we have seen about it. Airbag system we have seen. And missile control, even if 1 millisecond, 1 degree angle error will lead in large errors in missile control. So it is very difficult to control missiles. Flight control system, solar tracking system, ship steering system, tracking of robot arms in welding, all these comes under applications. In quantum control now, the new area is quantum control, where we are going to control in the atomic level. India has announced a budget of rupees 8,000 crore for quantum control and cyber physical system. This is the future. If you want to further know about it, you can go on dst.government.in and you can see what is cyber physical system. Cyber physical system is computationally intensive decision making on mechanical systems. So we have a lot of computations in the cyber physical system. Reference for reading, R.C. Dorff and R.H. Bishop, Modern Control System, 10th edition. You can use it for reference for this one.